Hello, today we are going to talk about colorimetry. Before entering into this topic, I ask for your support with a like so then the video can reach a wider audience. I hope for your support. Okay, colorimetry. Colorimetry is the analytical method in which we use a visible light spectrum. It's an analytical technique used to determine the concentration of colored substances by measuring absorption of visible light. So here in this figure, we can understand the general mechanism of how this method works. This figure shows us how the colorimetry analysis is carried out. There is the source of the light, which is filtered by some filters, and the filtered spectrum of the light is absorbed through the samples, and the transmitted light is identified by the detector photocell. So then the transmitted dose of the light is used to define the concentration of the compound that absorbs the light. This is how the colorimetry works. Okay, here in this photo we can see that different electromagnetic waves are used for different, let's say, intentions. Radio waves are used for amplitude modification radios or frequency modification radios, and microwaves are used for heating processes used in microwave ovens. Infrareds are used to detect the thermal infrared imaging kind of temperature-like means. And ultraviolet are used for different methods, and we talked about the X-rays and gamma rays in other videos. So today we are going to talk about the visible light spectrum that is used to determine the concentration of compounds that develops different colored complexes or just compounds. Uh, Let me remind that the visible spectrum differs. I mean, the visible spectrum widens from 380 to 780 nanometers. In some cases, we can say from 400 to 800 nanometers. Again, that 20 nanometer difference is not something significant. This is the visible spectrum that is used for colorimetry analysis. Here in this photo, we can see historical background of colorimetry tools that the past development of optical analysis methods, early color comparison techniques, and here we can see modern digital colorimeters. Okay, these are these simple first tools that gave the development to further uh, trials of colorimeters, and further they were started to be used by using electricity, and the next generations developed looks like this, that used this kind of tools, mechanical tools that could show us the level of absorbance. And further, even the absorbance detectors were digitalized. I mean, this kind of displays are used today in modern colorimeters. And today we even have this kind of portable, simplified colorimeters that can be used in agriculture, in environmental studies, and some other disciplines of research. Okay, some people sometimes might misuse colorimeters or spectrophotometers. Now I'm going to provide some simple differences between them, even if they are kind of overlapping pointers of spectrophotometry and colorimetry. There are some strict differences between them. First, colorimeters use filters, spectrophotometers use monochromators and a wider wavelength range. We are going to talk about it a bit later. And other differences between them are that spectrophotometry uses the electromagnetic waves differing from 200 to 800 nanometers, and colorimetry uses only the visible spectrum, as we talked earlier. Wavelength is selected by using monochromators in spectrophotometers, and colorimeters are mainly equipped with filters that might filter some short spectrum of the color. Okay, and spectrophotometers consist of a sensor, data processor, and computer, and colorimeters are equipped with sensor and data processor. They are usually not linked to computers. Uh, since spectrophotometers are equipped with some complex mechanisms, they are more expensive and they are more sensitive, and colorimeters are kind of primitive versions of spectrophotometers, and that's why they are not as expensive as spectrophotometers, and they are expected to be less sensitive compared to spectrophotometers. And this is about the interaction of light with matter. In general, we can expect that the interaction of the light with the matter can include the reflection, absorption, and transmission. And in detail, they can be not only absorption, transmission, and reflection, but also the interaction between the light and matter can include the emission and refraction. And in our earlier lectures, we talked about some of these terms. And today we are going to talk about only the absorption. Absorption is the type of the process that some portion of the light is absorbed by the matter. If the matter is kind of liquid, so the level of absorption of the light is expected to be more compared to solid state matter. Okay, and on the other hand, the absorption might cause heat. So this is about physical interaction between light and matter. And mm, the main topic that the main point we need to understand is that the light developed between the reactions of two compounds forming some color reactions, and color compounds might have some highest, let's say, point peak of the absorption. Here we can see that the Lowry method has 750 nanometers as the highest point of absorbance. And in Bradford method, here we can see that the highest absorption belongs to 600 nanometers. So this thing is mean that we need to follow the protocol while we are carrying out colorimetry analysis. If we want to modify or develop some new methods, we will need to see the absorbance curves, absorbance levels of the light by using different wavelengths. Even if these processes are done by using spectrophotometers, but they help us to develop the colorimetry methods, colorimetry analysis. So this is about different colors and different absorbance. I would like to highlight that the blue color is about 400, let's say, 400, 450 nanometers. I mean, this blue color. But here we see that the blue color absorbs from 600 to 750 nanometer wide spectrum, which means that the color and absorbed light differ from each other. My point can be better understood by this figure. Um, that blue solution absorbs orange light, yellow solution absorbs violet light. We know that the visible spectrum starts from violet from 400 to 450 nanometers and ends in dark red color ending at 750, 780 nanometers. So if we make this kind of circle, then we can find out what kind of colors of the solution can absorb what kind of wide spectrum. As we discussed, that blue colors absorbs orange color, about 500, about 600 nanometers. Blue color, 600 nanometers. Okay, let's take a look at these results. Blue color, yeah, blue color and 600 nanometers. And this can be a kind of example to understand the proper results that we explained in this website. And yellow solution, as indicated here, absorbs violet light. This is also in accordance with this explanation. Uh, Let me remind you that this is not something strict, because here we can see that blue color in case of Lowry reagent absorbs 750 nanometers as the highest point, but 600 nanometers are also kind of higher point compared to blue or green, I mean yellow and other colors. So these are the pointers that we need to understand, that there is this kind of linkage between the color of the solution and the absorbed light spectrum. Okay, there is a law termed Beer-Lambert law that states that the absorbance of the light is directly proportional to the concentration and path length. Here, it is expressed by the equation A equals ECL. A is absorbance of the light, E is the molar absorptivity. It's a constant for each substance that could be given exact wavelength, and C is the concentration of that compound that develops some different colors, and L is the path length. Here is it is the length of the cuvette. Here we can understand that the absorbance of the light in the first cuvette might look like this, that some of the light is absorbed here, so the dose of the light reaching here the second cuvette is much lower, and the level I mean the dose of the light reaching this cuvette, the third cuvette, is much lower compared to this one. This means that the absorbance is happening in these first two cuvettes, so then the dose of the light reaching this point is much lower compared to this one. And I'd like you to pay your attention the higher level of scattering here in this case, and here it's lower, and here it is even lower. That we can understand that the absorbance is really directly proportional to the concentration of the drug on one hand, and on the other hand, it is directly proportional to the length of the dish, in our case cuvette as well. Okay, next. When we carry out colorimetry analysis, we need to develop calibration curves. And this is about the graphical representation of calibration curves. It is about the absorbance and concentrations. And as the concentration of the compound is high, the absorbance level is high here. We can see that the concentration of the compound is low, so the absorbance is low. As the concentration of the compound is high, so the absorbance level is high. And in all these 5-6 cases, we can see similar tendency. Another point I would like you to take into account that not all cases we can see this kind of tendency that reaches the 0 point. Okay, in this and these cases, we see that the calibration curve is reaching 0 point, and here as well. But it's not for all reactions. Here we can see the line is not towards zero, and here even if it's not shown here, it's also not towards the 0 point. So this means, okay, these are the points that we need to take into account as well. And another point I would like you to pay your attention to is that the minimum and maximum points of the concentrations should be at least 6-7 times differ. Let's take a look here in this example. Okay, the concentration is 1.6 milligram per milliliter, and here it's 11.2, which means, okay, I don't know how many times, about 7 times differences. And here we can see that if this point is 1, okay, this is some like 6, and this should be 1. If this is 1, okay, here we can see it's 10, so 10 times differences between the minimum and maximum points of the concentration were taken. So these are the pointers that we need to pay some special attention while we are developing our own graphical representation. I mean the calibration curve. And another point that we need to pay attention is that um, the absorbance should be not smaller than 0.1, and here we can see in different cases, okay, it was taken even 0.1, but for calibration it's better to take the range, range from 0.1 to 0.9. In some pharmacopoeia, there are requirements that the pointers should be between 0.3 and 0.7. If the uh, if the absorbance are between 0.7, 0.3 and 0.7, that's fine. But at least they should be between 0.1 and 0.9. Okay, if it's lower than 0.1 or higher than 0.9 or 1, so the peer review processes might face some difficulties. I mean, the experts might have some comments that might cause the rejection of your results. So please take into consideration these points while you are developing your own calibration curves. And here we can see basic colorimetry components. They are equipped with a light source, as I spoke about. They are equipped with filters, sample holders as shown here, detectors, it should be inside somewhere, it's not shown here, yeah? And displays are shown here, and turning on off points can be equipped and can be provided, and transmitters control can be provided in the modern equipments, and wavelength control is the points, as we talked earlier, that in colorimeters different filters are used, and spectrophotometers, the monochromators light sources are provided. Okay, and this is about the light source. Okay, in colorimeters, as just I explained it, common sources include the lamp, which can be further filtered, and the lamps are equipped with a tungsten filament. As we know, the Edison bulbs also contains this kind of tungsten filaments. This is the source of the light that could be used in colorimeters. Okay, inside is provided with inert gas in order to provide long time utilization of the lamp. Okay, colorimeters involve quantitative estimation of colors. The difference in color intensity results in the difference in the absorptions of light. As shown here, the intensity of color is directly proportional to the concentration of the compound being measured. Okay, here there are some condensers that could collect the light to a smaller, let's say, surface, which is further filtered. So then some light can be filtered, and based on the absorption and transmittance of the light, we can find out about the concentration of the compound. And here we can see the optical filters, which are used to isolate a specific wavelengths to improve the measurement accuracy. Here we can see if the if the since if the colorimeters are provided with some special filters, okay, the wavelength can be stimulated. I mean, the constructive interference can happen there. The filters uh, not only uh, not only not only filter. I mean, filtering process does not mean that only some exact amount of the light uh, is supported to be transmitted. I mean, the concentration of the lights that we do not need is reduced. This is the point. I mean, if the filter transmits, let's say, blue color, it does not mean the violet or yellow, green colors are absolutely absorbed. It means, okay, the blue color is blue color and transmittance is higher compared to other spectrum of the light, as indicated here. These are the points that we need to understand. Okay, and here we can see the types of filters. They could be absorptive or dichroic. Absorptives are cost effective, and they are of wide availability, and they are scratch resistant. Excellent environmental and chemical resistance are provided to them. And dichroic ones are those that are provided with precise transmission, and they are capable for thin filter A wide variety of simple or complex types can be possible, but they are expensive compared to absorptive ones. On the other hand, absorptive ones are able only for poor transmission slope. They are not suitable for precision applications, and they are heat sensitive, and they are cost effective, but the cost effective might cause some disadvantages. These are the points, and here we can see how the green interference filter can work. Here we can see that when green color transmits, the red color and blue color are reflected. This is the point of how filters work. Okay, and this is about dichroic filters. Dichroic filters supports interference. They support constructive interference. Dichroic filters, also known as interference filters, they filter light by rejecting all undesired wavelengths, allowing selected wavelengths to pass through. And the term dichroic is derived from Greek word dichros, meaning of two colors. These filters are constructed using thin film technology by depositing several layers of dielectric film. On one side here we can see dielectric reflectors on two sides, and this is glass substrate. So this is the layers of this kind of dichroic filters. Okay, again they are more expensive, but the precision is higher compared to absorptive ones. And these are about the detectors that convert transmitted light into electrical signal. We talked about light source, we talked about filter system, and this text is about photoelectric detectors. And their function is detecting the light. This detector transforms the intensity of emitted light into an electrical signal. The electrical output matches the sample scalar attributes. And ideally, the compound response, the combined response of the light source, filters, and detector should closely resemble the spectrum sensitivity of the human eye to a certain illuminant. And getting a perfect match between the instrument response and human eyesight is difficult. However, high quality three stimulus colorimeters provide an accurate approximation. Notably, the mismatch occurs often in the short wavelength band. And mathematically modifying the measured blue value in proportion to the green value, Y creates a more accurate total value. And another name for photoelectric detector is photocell. Photocell in a colorimeter measures the intensity of light, as we talked. Located after the sample cuvette, it detects the light that hasn't been absorbed, that has been transmitted. And according to Beer-Lambert law, okay, we can find out about the concentration of the compound based on the level of transmitted light. Okay, this is about, these two figures are about working principles. Uh, as we talked earlier, okay, the colorimeters are provided with light sources, filters, as shown here. Lenses are provided to condense the light, as shown here. And then, okay, here we can see the absorbance and transmittance of the light, and photocell or detector helps us to digitalize the level of the transmitted light. And again, about the colorimetric standard curve that we said, the minimum and maximum points have to differ from each other at least 6-7 times. And measuring absorbance of unknown sample requires developing this kind of colorimeters. Again, Okay, the best range for colorimetry analysis is between zero point 0.3 and zero point 0.7 for absorbance. And if you are not able to find that, you have to be between zero point 0.1 and zero point 0.9, as I explained it. Okay, and these are about the example analysis, determination of iron using thiocyanate complex. Okay, this kind of points were developed in the research paper given in this website. Uh, I mean, this is quite linear, highly linear, not quite highly linear, let's say. And the ask weight level is also very high, almost very close to the required levels of ask weight for HPLC analysis. And here we can see that the calibration curve can be affected by different pH here. The pH at 2.8 resulted 99.38. When pH was increased to 3.2, okay, the absorbance was about 100.5. So these are the differences that might be quite short difference. I mean, this is something that could be accepted, and the concentration of thiocyanate also did not cause some big differences when the concentration of it differ from 7.8 to 8.2. So the differences were even smaller compared to this one. And the effect of temperature was also not some significant. Uh, this is another point that should be taken into consideration while developed the calibration curve. And the reaction time, here we can see 99.12, 99.0. So the difference for 4 minutes is not something significant. So these are the pointers that we have to pay some special attention while we are developing our own calibration curve for the methods we are dealing with. And these are about the application in clinical chemistry. In clinical chemistry, okay, colorimetry is widely used for the quantification of glucose, as shown here, for hemoglobin analysis, for protein analysis. I mean, the colorimetry is one of the most practical methods in clinical applications. And here we can see that the colorimetry is also widely used in environmental analysis for methylene detection or water pollution monitoring, as shown here. This kind of method was developed. The addition of mercury ions caused the difference in the color intensity that could be used to quantify the concentration of tungsten ions. And here we can see that the compound termed FL1, which is a bidentate ligand, which binds through nitrogen of the imine group and sulfur of the thiol group, had uh, this kind of colors with different ions. With iron ions, it developed this kind of brown, all brown light colors, and similar color with less intensity was found with cobalt, as shown here, or with copper ions, and with tungsten. This kind of color was developed. And in other cases, we can see that that compound developed kind of similar colors with chromium plus 3 ions, or vanadium plus 5 ions, manganese plus 2 ions, magnesium ions, lead ions, zinc ions, nickel ions, or aluminum ions. The colors intensity were quite similar, and the colors were also similar, uh, which means, okay, if this kind of colors developed, it is possible to propose that the concentration I mean, the total concentration of these ions can be kind of quantified, quantified based on the calibrations that could be developed by using various options developed by the mixtures of these colors. Uh, I mean, the colorimetry has advantages and disadvantages. If this kind of color, okay, forms, okay, we can propose high concentration of iron ions here, or if it is something like this blue color, okay, we can propose high concentration of um, this ion, mercury ions, but this kind of colors might enable us to develop kind of high concentrations of one of these ions, or a mixture of these ions. Okay, in food chemistry, they can be widely used. This is another example. Here, I would like you to pay your attention to the R squared, which is also quite high. And the authors also highlighted the precision and accuracy that were in accordance with the validation guidelines. If the results are shown to be valid in different time intervals, or in some different pH intervals, so then the method can be accepted by a wider audience and can be more popular, that could be used. Okay, here we can see the advantages: that the colorimetry is simple, low cost, fast, it can be carried out fast, and it is good for routine measurements, but the limitations include that only color compounds can be analyzed with them, and interference from the turbidity might cause some differences, discrepancies, and lower sensitivity, as we discussed, compared to spectrophotometry, and related errors resulting from improper calibration of dirty QS or instruments instability might also cause some kind of discrepancies or differences between the results obtained by two different experts, or by the same experiment in two different tools. Okay, these are about the advantages, limitations, and related errors. And in summary, we say that colorimetry measures light absorption to determine the concentration of colored substances. And these are all. I express my thanks to you for watching, and I kindly ask you to support us with your likes so that the videos can reach wider audience. And that's all. Thank you for your attention. Have a good day. Bye.